In this math counts preparation lesson, we're going to be talking about some circular geometry. We're going to be talking more about triangles and doing more of the advanced geometry problems found in math counts. So let's get started. So we're going to start off the video with just circular geometry, which we're going to start off with just tangents. Right now, tangents, there's not, and the problem we're going to look at today is not really, you don't really need to know anything about tangents, but we're talking about circular geometry, and you deal a lot with tangents. You deal in school level, chapter, state, national, so you need to know your properties of tangents. First off, this is the two-tangent theorem. So basically, if I have a circle, right, and these are external points, like this. So basically, the external points is like if we redraw a circle, like I'm gonna give a better example. Like a good example of this is like if I start off with a right triangle and I inscribe a circle inside of it, and then I start the radius of a circle and I draw radii like this. Now from here, this is a good application of a two-tangent theorem because two-tangent theorem is like this. So basically, let's forget about this whole right triangle thing. So two-tangent theorem is basically like over here. So these have to be equal in length. Let's call them x. And the two-tangent theorem states that these are external tangents, and these are coming from the same external point on the circle. So these have to be equal. That's one of the properties you need to know. You also need to know that, suppose we have a circle P. If we draw, and if we have another point over here, point Q, and we have a line L, which point Q lies on line L, then if point Q lies on line L, well then, now let's draw in a radius. So let's draw in PQ, segment PQ is a radii. It's a radii of circle P. And if I draw this radii, you'll notice that it forms a right angle over here. And this applies to any tangent. So basically, a radii drawn to a point of tangency makes a right angle. And this is useful in whenever you have I'm going to give an example. Like if we have a square and I just put a circle inside of it, assuming, and I know this isn't drawn the best, but if the circle is tangent to all sides of a square, I'm going to draw a better one. So if the circle is tangent to all sides of a square, then it's useful to use this application right here and draw radii. And this can help build right angles. You can build a small square in here with R. So it's useful applications of the tangents. That's basically all you need to know when it comes to tangents. This one is actually useful whenever you're dealing. It's good to know the two-tangent theorem, so I'm just going to label these. So these are just your properties of tangents. And then we have, some people might call this an application of power of a point, which you don't need to know power of a point for chapter level math counts, but this is two-tangent theorem, which some people might call it an application of power of a point, but you don't need to know. If you don't know what power of a point theorem is, then you don't need to worry about that. Two-tangent theorem. That's all you really need to know when it comes to circles. When it comes to tangents, what I meant. Now when it comes to angles, let's go to inscribed angles, etc. So angles, we're gonna be dealing with some triangles today. And triangles. This is again related to circles, so if I start off with a circle and I in the center, and then I just have a chord maybe over here, you can see how I can just form a triangle like this. And it's easy to make congruent triangles and whatever, similar triangles within a circle, because it's easy to have triangles like this where these angles are like equal. It's like theta, and these angles will be equal. So basically that's how you can use the similar triangle inside of it. I'm gonna just call it X because why not? So basically these are equal angles. And it helps in like similar triangles and stuff. You can also always like right triangles are easy to build within circles whenever you have tangents. So like if I have assuming this is like a straight line, and then I have another line which is tangent to the circle, goes like that. Then I have another line, and then I have another line that's tangent to this point of the circle. You can see how it's easy to build a right triangle. We can start at this radius, start at the center, then just draw in a radii. That's a right angle. And now you can't really build a right triangle within. Like there's one way you can try, and there's one way you can, but it has to be within a semicircle. But over here, if you want it to go from this point to this point, you can just draw it, and then you can just draw the hypotenuse in. That's the easiest way whenever you're dealing with the problems. Or if you want to inscribe it within the circle, you can only do it within a semicircle, and this is because of inscribed angles, which, if you don't know inscribed angles, like, I'm going to give an example. If I have an inscribed angle, let's say, I'm not really sure how to do this, but like, inscribed angles like this, maybe? Never mind. So, you don't need to know about that yet, but an inscribed angle is the reason we can, because like, essentially, the arc measure of this semicircle is a 180. So this is how you would form it, basically. You go to this tangent right over here, and this tangent right over here, and you would just draw, and then this would form a right angle, and this would be your hypotenuse. And this is because this is actually what I was going to talk about over here. If I start from over here, like, this was actually inscribed angles, like something like this, and this is like the arc measure. So if the arc measure of this is like, I don't know, like, let's say it's 60 degrees, and this is 30 degrees, this angle right here. So that's basically inscribed angles, and the reason is because this arc, we know it's half, so the circle has 360 degrees, so half of it will have 180 degrees arc, and then that means that this angle has to be a right angle, since half of 180 is 90. And our problem will require another useful formula, which we will discuss within the problem itself. I won't tell it to you now because it's an interesting formula. So let's get into the problem. But actually, yeah, so let's get into the problem. So this comes from the 2018 Math Counts Chapter Sprint Round. It's number 28, so one of the harder problems in the test. So in Circle P, let's start with a picture because we didn't get a picture on this problem. So I'm going to start with a picture. This problem, we're going to do a picture. Could be a big picture. Okay. Circle P. We're going to label the center as P because that's what it is. We have chords A, B, and C, D. So I'm just going to like do a rough sketch of what this might look like. So like, we have chords A, B. So like, we might have A. We might have A right over here. Right, like this is A. And then we might have like B maybe over here. And we can just form a chord by just drawing a line. And then we have C, D. And they intersect at E. So maybe I'll have C over here. And then D up here. So D could be up here. Again, this is not to scale at all. I'm just doing a rough sketch. Because this is actually hard to do like a full, like, accurate sketch. Because there's so much going on. So, okay, and they intersect at this point E. So I'm going to call this E, the point of intersection. And we're given some side lengths. So AD equals AE. So When I said this wasn't to scale, I really meant it wasn't to scale. So we're going to draw a segment from A to D. So this is AD. So because this is really not to scale, like if you just see how this is going to look, AD is equal to AE. Like this is not, these do not look equal, but they're just equal and they're both 3. So I'm just going to label them as 3. Even though we know like to scale they don't look equal, but these are 3. And then ED is 4. Just give us a rough sketch of the problem, and I don't think we need to label P because that's just extra writing. So we have circle P. Start off with A, start off with B, and then I have this AB, and then over here we have CD, so I'm going to draw C, then D up here somewhere. Kind of do a rough sketch of the problem. They intersect at E. And then we can just draw this segment AD. And we know AD equals AE. They're just 3. So this is 3, this is 3. I know they don't look alike. ED is 4. So ED is just 4 up here. And then we know that BC is 5. So BC is 5. And let's see what that comes in. Oh, BC right over here. Okay. So I'm going to bring out the eraser, and we do not need this. Okay. So we know that BC is 5, so I'm just going to draw the segment in. BC is 5. And we want the area of triangle BCE. So this is an interesting problem, because first off, the picture was not that easy to draw, and we know we messed up here because it doesn't really look isosceles, but we have an isosceles triangle, we have another triangle, and these are equal angles since they're vertical angles, so we can mark these equal angles, and, well, these are equal angles. Well, these are similar triangles. These are similar triangles because the proportions, we look at the proportions, they have to be the same because BE and CE have to be equal because they're coming at an intersection of the arcs we talked about over here. So basically, you should always note that triangles like this, we can just use some similarity to find that the angles, at least 2 angles, are equal because we have these parallel, well, not really parallel, but they're going this direction, so these have to be equal angles, and 2 angles are equal, they're all equal. Well, these are similar triangles, so we can use similar triangles to solve the problem. So let's go ahead and use similar triangles. We know that BC corresponds with AD. So we know that BC corresponds with AD, and we have a ratio of 5 to 3. So we know that BC to AD is just 5 to 3. So essentially all the triangles are in a 5 to 3 ratio if we consider the bigger sides to the smaller sides. So the ratio is 5 to 3. And we can use that for everything. So in this case, the smaller sides, we're going to use the, and since this is 5, we know that 5 corresponds with 3. That means that this must be another 5. And I know this is not to scale, but this is another 5. So these are both 5. And then what else do we know? We know 4 is the smaller one. So we know 4 to the big one corresponds with 5 to 3. So we know that we can just solve the proportion, and we get 3 times the bigger side is just equal to 20. So the bigger side is just 20 over 3. So we can conclude that this piece is 20 over 3. Right, so 20 over 3 is this. Is this BE. And now we want the area of triangle BCE. Here's where that interesting formula comes in. You're probably familiar with half of base times height. That's the formula for the area of a triangle. Over here, the base could be 5, 3, or this 20 over 3 over here. We don't know the height, and the height would take a while to find out. I don't think you can find the height, and given that this is the sprint round, I don't think we would have time to go ahead, find the height, and then plug it into our half base times height formula. Now don't get me wrong, that formula is the fastest way to find the area of a triangle, but here we know the side lengths, but how do we find the area just using the side lengths? That's where we need to talk about Herons Formula. Now we can just heron this to solve the problem. For those of you that knows Herons Formula, you can just skip ahead. You can just heron this. The real part of this is just putting all of the picture, drawing an accurate diagram, labeling up the diagram, and then you can just apply Heron's Formula. So Heron's Formula is a simple formula which you do not need to memorize because it is this simple. It sounds scary looking with the S and the A, but I want to make it so simple, you're going to think this is the most simplest explanation of Heron's Formula. So I'm going to make this simple. I'm going to say we have a triangle with side lengths of A, B, and C. Okay, it doesn't matter what A, B, and C are. Let's say they're just integers. Okay, they're anything. They're just real. Okay, they're just real numbers. And I say, and to find the area of this, I can just sum up A, B, and C. And you might call this the perimeter, but I'm going to do something even better. I'm going to divide the perimeter by 2. And we call this the semi-perimeter. And we're going to denote the semi-perimeter as S. Right? We denote the semi-perimeter as S. Now we're going to take this S. And we're going to take the difference of the semi-perimeter from each of these sides and just multiply them. So we're going to take the difference between S and A. And then we'll multiply it by the difference of S and B. And then take the difference between S and C. So simple. And then we just take the square root. Take the square root of this and we're done. This is Heron's Formula. You don't need to memorize this. Just remember, take the semi-perimeter, which is you just take all the side. You just take the perimeter, divide the perimeter by 2. And once you've divided that perimeter by 2, well, then all you need to do is just take the difference from all the sides, and you're basically done. That's Heron's Formula. We can just heron this thing, and we'll be done. Let's just heron this thing. So first we're going to take the semi-perimeter. So 5 and 5 give me 10. So now I need to just add some fractions. I have 20 over 3 plus 10 over 1, which I'm going to rewrite this with a common denominator. So 1 times 3 is 3, 10 times... this is just a 30. So when I have this, I have 20 and 30 give me a 50 over 3. Right, so now I have 20 and 30, which give me 50 over 3. And this is the same as just, since 30 over 3 simplifies to 10, so this is just the same thing. And now we have the perimeter, so now we just divide it by 2. That's the same as just multiplying it by 1/2. And this cancels out, leaving a 25. So we have a semi-perimeter of 25 over 3. And now we know our semi-perimeter. So now we can just take the semi-perimeter, 25 over 3, and then we can just subtract off some of the side lengths, so we can just find the difference. So first I'm going to take the semi-perimeter, which I already have, and now I'm going to take the semi-perimeter and subtract off this 20 over 3. But when I do that, I'm left over, I take 25 over 3 minus the 20 over 3, and then that just leaves me with a 5 over 3. Right, so I have a 20 over 3, well, and I must multiply that by 5 over 3 by Heron's Formula. So you can just heron this. Minus 20 over 3 leaves me a 5 over 3. And then I just take the difference. I take 25 over 3. And we can erase all of this to give us some more room. Similar triangles also made the problem a lot easier, as you saw. So always use similar triangles. We've covered a lot of similar triangles in the preparation lessons. So this is a 5 over 3 that we have over here. Now we know the semi-perimeter is just 25 over 3. Now we can take the 25 over 3 and just subtract off the 5 over 1. Right, so I can just take off 25 over 3. But guess what I'm going to do? I'm going to take 25 over 3 and I'm going to subtract off a 10. But then I'm just going to do that again. So I'm just going to double it. So essentially, just want to take away the 5 over 1. And this leaves me with 25 minus 15 over 3. Give me a 10 over 3. So multiply that by a 10 over 3. I'm going to go through the same process, so another 10 over 3. And now we have something cool. We have 25. We have this massive product. Now, I'm going to do something I'm going to do something cool. We're going to take this 5 over 3, and then we're going to take away the 5 over 3. So we're going to start with this 5 over 3 over here. So I'm going to start with the 5 over 3, and we're going to multiply this out. And then over from there, we just take the square root, simplify, and then we have the answer. So now, I can just take this. So I take this, and we have 25 times 5, give me 125. Over 9. Over here, I have 10 times 10 is 100. Over 9. And this is what I have. So now I can take this, I can multiply. This is an easy product to compute. I have 125. I slap on the 2 zeros, and the denominator of 9 times 9 is just 81. And the last step is just take the square root of the entire thing. Now the square root of the entire thing, that's just taking the square root of the top, and then the square root of the bottom. Square root of the bottom is just 9. Square root of the top, it's not a perfect square. We need to simplify that perfect square. Now when we're simplifying this perfect square, we can see that something needs to divide this. So I know that 25 divides it. Right, so 25 divides this. That means I have 25 times something. So I know that 25 times something gets me to this. So 25 might divide this, it might not. 25 times 5, so I see a 500. Well, 25 times 5 is 125. Slap on the 2 zeros, we have our thing. So now we have this 25 times 500 is this. Now, 500 is obviously not a perfect square, but this is. So we can just call this 5, and we can multiply that by this. So this is basically 25 times 500. We can rewrite this as a product, and this is just 5 root 500. So if I square the 5, I'm going to get that. Now the square root of 500, we're not alone. We can simplify that as well. That's just 25 times 20. And 20 can be broken up into another product with a perfect square, another number. And 25 is a perfect square already. So let's break this up. So this is just, this number right over here can be broken up again. So this is just 25 and 20. So we have 25 and we have 20. 25 is a perfect square, so this can be written as 5 root 20. Again, all we're doing is taking this and we're breaking it up. So we have 5 root 20, and we're multiplying that by 5. Don't forget that. So we're multiplying this by 5 since we still have 5 root 500. Now we have 25 root 20. And now the last step is to simplify root 20, which we hope might be the last one. 4 times 5 is 20, so that's 2 root 5. So you multiply that by 2 root 5. Well, no, we have 2 root 5 is, if you have 25 times 2 root 5, we'll have 25 times 2 is 50. And root 5 can't be simplified any further, so we have 20 times the square root of 5. So our final answer is just 50 root 5 over 9, which should be the answer. And that's how we do the problem. We just heron this, and as you saw, Herons Formula, pretty simple. We just heron this and got the answer. And as you saw, we applied similar triangles, we did lots of cool things, and got the answer. Now, you shouldn't need to memorize that Herons Formula thing. You should remember Take the perimeter, divide the perimeter by 2, take the difference in all three sides, take the square root of that, and you have the answer, which is right over here.